Hello. So this video, we will learn about the fourth equation, Maxwell's fourth equation of electromagnetics. So we have already seen three equations, and we have also seen that each equation begins with a particular law. The first, second, and third equation, they begin with a particular law. Similarly, we have a fourth equation for derived by Maxwell, which is also derived from a particular law. Let's go into it. So Maxwell's fourth equation. So this begins with what is known as Ampere's law. Okay, this begins with what is known as Ampere's law, wherein it is given so line integral of h dot dl is equal to I. This is obvious. Changing magnetic field along this direction will produce one I, which is perpendicular to it. We have seen that. Magnetic field, electric field, they are all mutually perpendicular to each other. So, and we also know that surface integral of j dot ds is equal to I. How does this come? Maybe your question. J is the current density. So, current density is given by current divided by area, or you could say I is equal to J into A. If A is equal to S, let's say A is equal to ds, then my I would be given by J dot ds. That's what I have written here. Now, equating these two, what will you get? Line integral of h dot dl is equal to surface integral of j dot ds. So now I am going to apply now Stokes theorem. By Stokes theorem that we have done in the last law itself. So I could write that line integral of h dot dl is equal to surface integral of surface integral of curl of h. Surface integral of curl of h into ds. This is what is Stokes theorem. You have already seen it. So I am going to substitute this in place of this. So what will I have? I will be left with del cross h into ds is equal to, this is surface integral obviously, I'll have j dot ds. So now, going by the same rules which we have gone earlier, both are surface integrals over an arbitrary area. So I could write del cross h is equal to j. Now what I am doing is, I am going to call in Gauss divergence theorem. I'm going to call in Gauss divergence theorem. So what does it state? Del dot del cross h is equal to del dot j. Now this del dot del cross h is divergence of a curl of a vector. So first we must find the curl of a vector, and then we must find the divergence of that product. Now when I say curl of a vector, it means, it's a vector which is changing in its angle. This is what it goes round and round and round and round. So if I want to find the divergence of this, it is 0, because this field is going round and round. No amount of field is leaving or no amount of field is coming. What is divergence? How it diverges, or it could alternately be also converges. Now you are looking at diverging, it is 0. So which means your left hand side del dot del cross h is equal to 0, which means obviously your del dot j should be 0, but your del dot j is not 0, because j is equal to I by A, there is current left, so j is absolutely not equal to 0, and this is not at all applicable for steady state. So which means you will have to bring in an extra condition. Now this del dot j is actually given by minus d rho by dt. J is the current density and rho is the charge density. The rate of change of charge density defines the current density. So del dot j is absolutely not equal to 0. So we are compelled to bring in a new term on the right hand side to balance the equation. So I am bringing in a new term. I could write now del cross h is equal to j plus jd, some random term jd. I am going to find the relationship for this jd. So now again I am writing del dot del cross h is equal to del dot j plus del dot jd. So this is 0. So I can now write del dot j is equal to del dot minus del dot JD. Am I right? So del dot J I have already seen is minus d rho by dt, which is equal to minus del dot JD. Or I could say del dot JD is equal to d rho by dt, because the minus sign cancels out on both the sides. This is one thing. Now this rho, the charge density, is also used in Maxwell's first equation, wherein it is given del dot D is equal to rho. So I could substitute that here. So del dot JD is equal to d by dt of del dot rho. I will do a little tweaking to this equation, and I can write del dot JD is equal to del dot dd by dt. Just tweaking this little bit. So I have del dot JD is equal to del dot dd by dt. D is the displacement vector, we know that. So you could write now, these are all okay. You could now write JD is equal to dd by dt. So we now have an expression for JD. We'll incorporate into the final equation for Maxwell's fourth law. So you will write del cross H is equal to J already existing plus dd by dt. So this equation is Maxwell's fourth law in differential form. So we are done with all equations of Maxwell, though they are in 4 different videos. I hope you integrate them and you are able to learn them. In case of any doubts, you can reach out across to me. Let's meet in the next lecture.